Hello and welcome everyone. My name is Chi-Chih from National Yangming Jiaotong University. Today, I am happy to present our work, FLORA, Fine-Grained Lowering Architecture Search for Vision Transformer. This research is a collaborative work with my colleague Yuan-Yao, Shixing, Ning-Chi Huang, and Professor Diana Marculescu and Kai-Chiang. Vision transformers have increasingly demonstrated remarkable capability in various applications, and its performance have become better and better day by day. However, we face a significant challenge on leverage this powerful model on the real-world application because of its growing computational cost. To alleviate this issue and allow the vision transformer to be deployed on the real-world application, this research tried to reduce the high computational cost of the VIT. Our solution is we will apply the fine-grained lowering approximation to compress the VIT model into a low-rank one. In this work, we successfully compressed the trending transformer model, DEIT, and swing transformer, and can yield up to 55% flops reduction. Before we delve into the detail of our methodology, we first introduce the low-rank approximation. Low-rank approximation is an compression technique that approximates the weight metric with a couple of low-rank matrices. Given a rank level R, we can decompose the pre-trained linear layer weight into a sequence of smaller matrices. By doing so, we can reduce the matrix size from m times n to m times r plus r times n. This can reduce the size and the corresponding computational overhead while maintaining essential information. To apply the lowering approximation onto the vision transformer, we have to carefully select a suitable rank level for each compression target to maximize the reduction of computational cost while maintaining the accuracy. However, this rank selection problem is non-trivial due to the huge search space induced by multiple compression targets. For instance, on the DITS, we have candidate rank level ranging from 1 to 384. Given that there are 12 transformer blocks and 3 target layers within each block, namely QKV, FC1, and FC2, the total potential combination is quite large. This immense search space made it clear that manual selection could be suboptimal, highlighting the need for an intelligent, automated approach to identify the most suitable configuration for applying low-rank approximation. To navigate such a huge search space and identify a suitable rank level for each compression target within the vision transformer, we novelly formulate the rank selection challenge as an architecture search problem. This is because selecting the rank level is analogous to selecting the low-rank architecture. In our framework, we begin by encoding the low-rank search space into a supernet. Then we move on to training this low-rank supernet, which in other words, to train all the low-rank architecture jointly. After finish the supernet training, we then adopt the evolutionary search for identifying the most effective architecture, which can yield us more computational cost saving. Thanks to the well-trained supernet, the performance for each individual low-rank architecture can be rapidly evaluated during the evolutionary search processes, which allow us to bypass the need for separate, time-intensive training process to evaluate a single architecture. To realize our low-rank architecture search, one challenge to overcome is how to effectively encode low-rank architecture search into a supernet so that we can train them jointly. To achieve this, we maintain a superblock which encapsulates all possible low-rank architecture for a given linear module. We call such strategy as weight inheritance. In weight inheritance strategy, for a given rank level Ri, the corresponding weight can be easily generated by inherit the top R vector from the superblock. This strategy enables us to encode different low-rank architecture within a supernet. Knowing the way to build the low-rank supernet, we now introduce how to train the low-rank supernet. Initially, we begin by factorizing the pre-train weight. Then, in each training iteration or mini-batch, we sampled a rank configuration, which contained rank level for each target. With a sample rank config, we can generate the corresponding low-rank architecture via the weight inheritance technique that we have just introduced. With a sampled and generated low-rank architecture, such architecture are undergo training, and the gradient are updated back to the active segment of the shared superblock. We repeated this iterative process for several times until the convergence. After several rounds, we can get the low-rank supernet. In designing our low-rank supernet that ensure all the encoding architecture are well trained, we confront a challenge of undertraining. This issue emerged particularly when the number of architecture that we are going to train together exceeds the capacity of our limited training iteration. Given that our supernet operates on a weight sharing principle, instability in the gradient update, especially from those architecture that significantly underperform, can adversely affect the training of the other. These observations have prompted us to design a strategy to filtering out the low-rank architecture that demonstrate poor performance to avoid the influence to the supernet training. Inspired by this, we try to design a methodology to do so. This is accomplished through a strategic block-wide analysis of the search space. By keeping the remaining part of the transformer block uncompressed, we evaluate each rank level combination one by one within each local search space. Then we can evaluate the accuracy drop of each rank level combination. Based on the insight that significant accuracy drop is an indicative of larger performance issue, the rank level with poor performance in the local search space can be dropped from consideration because when we jointly apply the low-rank approximation onto the remaining transformer block, such accuracy drop might become even larger. So, if we perform poorly in the local stage, then we should not considering when we jointly apply the low-rank onto the other. By applying such strategy to only transformer block, we can effectively refine the search space and allow us to focus more on saving our training budget to those potential architecture. After introducing the methodology of our FLORA framework, we now demonstrate the experiment result on ImageNet dataset to evaluate the performance of our proposed FLORA strategy. Here, we apply FLORA onto 4 different kinds of transformer model. Also, in the table of the left-hand side, we compare our FLORA methodology to various kinds of compression methods, including the token pruning, structure pruning, and also the multidimensional pruning, which jointly consider various kinds of compression target in a transformer. Here, from the table in the left-hand side, we can see a compatible or even superior result of our proposed FLORA to the other compression technique. Surprisingly, on the DITB, we can see up to 55% of flux reduction without any accuracy drop. When we compare to a non-uniform rank config, or also known as the manual design rank config, our searched fine-grained low-rank configuration can yield us extra 33% of flux reduction under the same accuracy. Overall, our result demonstrates significant flux reduction with only negligible accuracy drop on various kinds of transformer variant. Thank you for your listening.